Welcome to the start of Chapter 8, which would be our 5th unit of the year. This unit deals with rational functions. Our first section we're going to start with is going to cover the following targets. So write these down on top of your notes, please. After completing this lesson, I will be able to graph rational functions and also state the domain and range of rational functions. So what is a rational function? It's a polynomial divided by a polynomial. F of x equals p of x divided by q of x. So what are some examples? One example could be y equals x plus 1 divided by x plus 2. Y equals 5 over x. And y equals x squared plus x minus 6 over x cubed plus x minus 4. Now, the real key to this is the polynomial on the denominator q should not or cannot be a constant term, because then you're just dividing by a number. And that can reduce the fraction. That's not really a polynomial. So in other words, you need a variable in the denominator. Y equals 5 over x. The most basic of these up here is b, just because it's just x to the first in the denominator. These are the polynomials as numerators and denominators, with the denominator at least has one variable term. Thing also, think about when you're talking about rational functions, think about rational function, rational number. The rational number is a number that can be written as a fraction. Rational function is a function that's a ratio of two polynomials or a fraction of two polynomials. So we're going to think about it inconsistent with the idea of rational numbers. Okay, the parent function of rational function. Basically, the parent function of a rational function is 1 over x. It's the most basic. We're close to it on the last slide, 5 over x, 1 over x. It's the most basic form of a rational function that still keeps it a rational function. When we graph a rational function, the parent function is going to look something like this. And I'm going to erase that part a little bit. It approaches both the x-axis and the positive x-axis and the positive y-axis. And there's also a second part of the graph. That's not continuous. These parts do not connect, but they approach these x and y axis and on the positive side and the negative side, but do not cross them. Okay? These lines right here are what we refer to as vertical asymptote lines. And this one is what I call it horizontal asymptote lines. They box in the graph, so to speak. They kind of make a barrier where that graph does not cross those lines. It's really close, but does not cross. So vertical asymptote would be, well, what's the equation for the y-axis? The equation for the y-axis is x equals 0. So x equals 0 is the vertical asymptote. And the horizontal asymptote, well, what's the line for the x-axis? The equation for the x-axis is y equals 0. So y equals 0 is the horizontal asymptote. The functions have no values, so the parent function has no output values on these lines. Okay, they're the barriers. The asymptote lines are like the invisible fence that keep, you get an invisible fence maybe for your dog or pet, keep them in the yard. It's kind of the same idea. The invisible fence is the same thing as an asymptote line. It keeps the graphs from crossing into other areas of the coordinate plane. Our domain and range are then based upon what our asymptote lines are. Our domain is the x values. What's the only x value that you cannot plug into this function? Well, the only place where the x value has no output is on the vertical asymptote, x equals 0. So our domain is all real numbers, and this R with another line through it means real numbers, except x equals 0. And our range, well, what's the only value you don't get an output for? All is outputs above the y-axis and below the y-axis. I just don't get any y values on the y-axis, or excuse me, on the x-axis. So our range is all real numbers except y equals 0. So this is kind of the starting point. We're going to manipulate this equation. We're going to move it up, down, left, right, stretch it, shrink it, but we're going to do things to it based upon this parent function. Okay? The big thing to look at is the asymptote lines, are those imaginary lines the graph does not cross, and the vertical asymptote and horizontal asymptote directly correspond to the domain in the range. So, based upon the parent function, I said we were going to move things around or around the plane. One way we can write a simple rational function that's not the parent function would be to write in the form f of x equals a over x minus h plus k. The good news about this form, it's almost like a vertex form of a quadratic. Basically, it gives you your horizontal and your vertical asymptote. Y equals k, that's our horizontal asymptote. X equals h, that's our vertical asymptote. Now remember, much like we did with the vertex form in quadratics, to find your h, you take that expression in the denominator and set it equal to 0. So that's why x equals h is our vertical asymptote. It's the 0, if you will, of the denominator. Okay? So let's use that idea to see if we can graph this. We also have our graphing calculator, so have that handy if you have that at home. Let me show you how that can help you a little bit. So we have 4 over x minus 3 plus 2. F of x equals that. So based upon what we just looked at above, what is our domain range, vertical asymptote, horizontal asymptote going to be? Well, our vertical asymptote, remember, is x equals h. So to find our vertical asymptote, we're going to have to solve the equation x minus 3 equals 0. We add 3 to both sides, so x equals 3. So our vertical asymptote is x equals 3. We go over to 3 on the graph, and I'm going to draw a dotted vertical line. And I make it dotted because it's not part of the graph. It's kind of it's an imaginary line that we're just highlighting to show that that's the dividing point. So that's our vertical asymptote, or our imaginary fence, our vertical imaginary fence. Horizontal asymptote, we set up here, the horizontal was y equals k. Our k value is 2. So y equals 2 is our horizontal asymptote. So basically what we've done here is we've shifted the original parent function from the origin, from 0, 0, right 3 and up 2. Okay? So now what is our domain? What's our range? Our domain is all real numbers except, this is just another way to write all real numbers, x equals 3. I can't plug in 3. I go on the x-axis, 3 is the one that's got the imaginary line through it. I can't plug in 3. So my range is all real numbers. But why can I not? So we're going to put 7 like that. We're going to put 7. And all real numbers except y equals, well, we went up 2. There's a dotted line through 2. That means it can't be 2, and I can't get 2 as an output. And so that's our domain and range. So how are we going to graph this? Well, we're going to use our graphing calculator. So go to y equals, plug in your equation. The fastest way, like that button. hit alpha, y equals, and we can make a fraction here. So I'm going to put in 4 over x minus 3 plus 2. And we're going to graph it. And if I look, shrink it down a bit. If I look, I can kind of see that it looks like my asymptote lines line up. If I put it here, it looks pretty close. If I were to swing it out, it looks pretty close that it lines up. So I just want the general shape. If you really want to be picky, or you're running somebody that's really picky about getting some exact values, you go to the table, and I know I get some values to the right of my asymptote, my vertical asymptote line, which is 3. So 4, 6, and 5, 4. Over 4, up 6. And over 5, up 4. Now just connect the dots. Here's the graph. Then I can do the same thing for left of my asymptote line. I could do 1, 0, and 2, negative 2. So 1, 0, 2, negative 2. Connect the dots. Okay, and you want to show this as a curve, not almost a U-like curve, not quite, kind of like a bent U curve, really wide. But it's approaching, those arrowheads are approaching the asymptote lines, but they never ever cross them. Okay, so that's all I'm looking for when I ask you to graph it. How I want you to find the domain and range, vertical and horizontal asymptotes. Our last way to write simple rational functions, and notice all these functions have linear numerators and denominators. That's what makes them simple rational functions. Is of the form ax plus b over cx plus d. Now notice our h and our k went away, but we do have a way to find our h, so to speak, and our k, so to speak. Y equals a divided by c. Notice a and c are the leading coefficients of the numerator and the denominator. So a over c is our horizontal asymptote. And to find our vertical asymptote, we solve the equation cx plus d. In other words, what's the 0 of the denominator? Right? We take our denominator, set it equal to 0, and that's going to be the vertical asymptote, which makes sense. I can't have a 0 in the denominator. It was kind of the same way. Why does it, was it k in the, or excuse me, the way I worked out last slide, I made the denominator 0 on our last slide. So that's what the vertical asymptote is, where the denominator is 0. We can't have 0 in the bottom of the fraction. So whatever makes the bottom 0, we can't have. That's our vertical asymptote. So let's look at this equation. 4x minus 4 over 2x minus 1. Let's look at vertical. I always start with vertical asymptote just because in horizontal asymptote, that gives me a place to start. It makes it really easy to find my domain and range. Our vertical asymptote, well, vertical asymptote, they said, comes from cx plus d. So what's our denominator? Our denominator is 2x minus 1 equals 0. So I add 1. I divide by 2. I get x equals 1/2. So at 1/2, I'm just going to estimate it. That's right between 0 and 1. Put a dotted line. Horizontal asymptote. Horizontal asymptote. Remember, that's a over c. Well, our a and our c is 4 and 2. So y equals 4 over 2, which is just 2. Same as all we had in the last. So there it is. We've shifted right 1/2 and up 2. That's what this is done. What is our domain and our range? Well, our domain is going to be all real numbers, where x is not 1/2. Another way to write the domain. And our range is all real numbers where y is not equal to 2. Last thing we have to do is make a nice little graph. Go to y equals. And y equals, I'm going to simply, I don't want to have to retype in everything, so I'm going to delete some of this extra stuff we don't need. It was in our last example. And in the bottom of our fraction is 2x minus 1. So I'm just going to put that in. If I go in front of that x and I hit second delete, that's insert. And it lets me put a value in there. So 2x minus 1. On the top, we have 4x minus 4. So you may say, well, it's just easier to rewrite it. If you think so, then just delete it and rewrite it. That's fine. So, if I look at my graph, let's slide a version of it out here. A little bit. Looks like my asymptote lines hold up pretty well. Okay, I can go to my table and find some exact values. I'm just going to make a rough quick sketch. Make sure you show that your asymptote lines are the barriers that the graph actually approaches those but does not cross. Okay, and that is my graph. So looking back at our targets for today, did we graph the rational functions? I believe we did. We learned how to do that. That's the end of each problem. And we were able to state the domain and range of the rational functions, which were based off of what? Yes, they're based off of the asymptote lines. Okay, bring your notes for tomorrow. Be ready to work on the assignment in class. Have a good day.